In this problem, we're going to deal with kind of a classic example of trying to see what the largest, basically the largest square peg that we can fit into a round hole. And this is a common engineering problem where you have some sort of shape and there's nothing you can do to deform the shape inside of it to make it fit perfectly, but you want to see how big you can make it before it's just impossible. And so in this particular case, what we have is some rectangle bounded by the x-axis and this semicircle. So this is the circle of radius 3, but we're only worried about the positive case, or the y is positive case. So we want to figure out what the length and height, or you could say length and width, but basically the base and the height of the rectangle are to maximize the area, not the volume. And what you're going to find, I believe, in this case is it's not going to be a square. A lot of times the maximal area comes when you make a square, but because of the nature of this, if you make it a square, you leave a lot of area on these sides. So we want to grow it as much as possible. I think that's right, and we'll find out as we work it. So the first thing we want to do is we say, all right, what are we given? Well, we're given this. Well, what do they want? Well, they want an area. So I know that area is base times height. So that's some sort of height. And that's some sort of base. But if I think about it, if I have some sort of point here, then that has a coordinate x, y. So that tells me that this length has to be x, and this has to be y. And so that's x. So if I think about this rectangle, I really have 2x, y. Right? Because this length is 2x, and this height is y. And that's going to be helpful, because what we're given is this. Y is the square root of 9 minus x squared. So that gives me that the area could be rewritten as 2x square root of 9 minus x squared. Now that is a function of a single variable. Now that we have a function of a single variable, we can differentiate to solve the problem. So we can take a prime of x, which is 2 times the square root of 9 minus x squared. We have to use the product rule here, plus 2 times x times 1/2 9 minus x squared to the negative 1/2 times the derivative of the inside. So we have to use the chain rule here, right? Because the square root is like a 1/2 power. So we use the power rule we bring down the power. We subtract 1 from the power, but by the chain rule we have to multiply by the inside. So now we have 2 9 minus x squared. Now those 2's will cancel, so I'll end up with plus negative 2x squared over the square root of 9 minus x squared. So then I need to get a common denominator. Doing that, I get 2 9 minus x squared minus 2x squared all over square root of 9 minus x squared, getting me 18 minus 4x squared over 9 minus x squared. That's a lot of work. Now, the first thing we want to do before we go further is, let's think about our domain here. If we define it this way, then x can't be any less than 0, and it can't really be any more than 3, right? Because if it was 0, it'd be a straight line up, and if it's 3, it's just a straight line out. So it's somewhere, it's really not even less than or equal to. It's really these cases. And the reason why that's important is because if it's not even defined out to 3, because at that point you actually don't have a rectangle, you just have a line, then that means that plus and minus 3, you don't have to worry about them being critical points because they're not in the domain of the function, which is nice. We don't have to worry about it. So all we need to do is solve for where this is equal to 0. So x is plus or minus 3 over the square root of 2. But again, in this case, we don't worry about the case where x is less than 0 because it's not in the domain. So only the positive case matters. So when x is 3 square root of 2, we could take the second derivative test. Now that would be, can we not? Because the second derivative test would require you to do like a quotient rule there, and that's nasty. But what we can do is we can use that first derivative test where we take a value a little bit to the left of it and a little bit to the right of it. So a little bit to the left of this would be like 1 or 2. Let's see, 0.4, yeah. 1 would still be fine. If I plug in 1, I get 14 over the square root of 8. If I plug in, let's not say 3 because that's a little too far. Let's say like 2.5, so 5 halves. I get 18 minus 4, 25 over 4, square root of 9 minus 25 over 4, which is 18 minus 25 over, let's see, that's 36, so square root of 11 over 4 is negative 7. So it's positive and then it's negative. So that tells me it's increasing up until this point, and then it's decreasing after the point. So if it increases up to the point and decreases after the point, that tells me that this value is a maximum, which is good. That's what we're looking for. So if x is 3 over the square root of 2, now we want to plug that into our area function here. We say a of 3 over the square root of 2 is 6 over the square root of 2 times 9 minus 9 over 2, 6 over square root of 2 times 9 halves, which is 18 over 2, which is 9. So that tells me I get 9 if I plug it in there. Now, if I plug in these sort of endpoints here, like if I plug in a of 0, I get 0. If I plug in a of 3, I get 0. So that tells me that this has to be my maximum value because the points at the edges aren't my maximum. So then if this is one side, I still need to find the other side. I need to say, okay, x is 3 over the square root of 2, y is 9 minus 3 over square root of 2 squared, which is 9 minus 9 halves, which is the square root of 9 halves, which is also 3 over the square root of 2. Okay, so what you find is it doesn't actually end up being a square here. You have to be careful though. This is why it's important to kind of check your notes. That's why I went and checked my notes. And I got the right x value, but if I had taken this and plugged it into some homework assignment, it would have told me it was wrong. And the reason it would have told me it was wrong is because I solved for what the x value was, but that's not the width of the triangle. The base is 2x. So that tells me that this is 6 over the square root of 2, and this is 3 over the square root of 2. So you have to be careful there. That was my mistake. It could have cost me. So it's always important to refer back to your original schematic and realize that your base, that your original primary function is based on this base and height, not anything that you develop afterward.